Imagine you are debugging a massive issue. You try one fix, it fails. You read the error log. You try another fix, you run the test. It fails again. By the time you are on your 40th attempt, you need to remember exactly what you tried on attempt number 3 so you don't repeat it. Humans are generally okay at this. AI models, not so much. When an agent runs long debugging sessions across dozens of files and hundreds of actions, the context window fills up. Eventually, the information gets cut off. The agent forgets what it did 10 minutes ago. It starts looping. It starts breaking things it already fixed. It loses the thread of its own logic. The solution: hierarchical working memory. This is where Confucius changes the game. The Confucius SDK introduces 3 major mechanisms to fix this. But the most critical one is the unified orchestrator with hierarchical working memory. That sounds like a lot of buzzwords, but the concept is brilliant. Instead of treating the agent's memory like one giant chat transcript that eventually gets cut off, it organizes memory hierarchically. It partitions the agent's trajectory into scopes. Think of it like a senior engineer keeping a lab notebook. It doesn't just record every single keystroke. It summarizes past steps. It compresses the context. It preserves the important artifacts, the key design decisions, the patches that worked, the error logs that matter, while filtering out the noise. So, even if the agent is 100 steps deep into a problem, it can still access the notes from step 1 without needing the raw data in its immediate context window. This solves the amnesia problem. It stops the agent from spiraling into those loops where it tries the same broken fix over and over again. The 3 axes of design. The team behind Confucius organized the SDK around 3 specific axes: agent experience, user experience, and developer experience, agent experience. This is what we just talked about. Controlling what the model sees and how the context is structured so it doesn't get overwhelmed. User experience. This is about making the agent understandable for us humans. It provides readable traces and diffs so we can actually see what the bot is doing. Developer experience. This focuses on observability. It allows engineers to debug the agent itself, treating the agent like a system that can be tuned. It's a holistic approach. They aren't just trying to make a model that codes. They are trying to make a system that thinks and remembers like a coder. Part 3. The Underdog. Abu Dhabi's Falcon H1. Now let's pivot. While Meta was redefining how we structure agents, a research institute in Abu Dhabi called TII, Technology Innovation Institute, decided to redefine what a small model can do. They dropped a model called Falcon H1R-7B. Let's break down that name. The 7B stands for 7 billion parameters. In the current landscape of AI, 7 billion is tiny. It's lightweight. It's the kind of model you can run on a decent consumer laptop. Usually, models this size are good for basic chat or summarization, but they fall apart on heavy reasoning or complex math. But Falcon H1 is different. It is a reasoning model, and it comes with a staggering feature: a 256,000 token context window. Why context matters? To put that number in perspective, many standard models struggle once you pass 8,000 or 16,000 tokens. 256,000 is enough to fit entire books, massive code bases, or huge legal documents into the model's working memory at once. But here's the kicker. Usually, when you make the context window that big on a model that small, the performance tanks. The model gets lost in the data, but Falcon H1 is outperforming models way bigger than it. The architecture twist: how are they doing this? Well, reports suggest they aren't using a standard architecture. It appears to be a hybrid model. While the exact details are complex, this usually implies they are mixing standard transformer layers with something else, potentially state space models like Mamba or similar efficient architectures, that allows them to process massive amounts of information without the computational cost exploding. This is a huge signal to the industry. It proves that you don't need a trillion parameters to be smart. You need the right architecture and the right data. Falcon H1 is punching way above its weight class, specifically in reasoning tasks. It's a reminder that innovation isn't just coming from Silicon Valley. Abu Dhabi is playing for keeps. Part 4. DeepSeek's Technical Dump. The Open Box Moment. Now, speaking of innovation coming from unexpected places, we have to talk about DeepSeek. If you follow AI, you know DeepSeek has been disrupting the market by releasing powerful models essentially for free. But this week, they did something unprecedented. They updated their R1 paper. Now, usually when a company updates a white paper, they fix a few typos, maybe add a new citation. DeepSeek added 60 extra pages. The paper is now something like a secret technical dump. It reads less like a marketing document and more like a leaked internal manual. The open box philosophy. We often talk about black box AI, where we know the input and the output, but we have no idea what happens inside. DeepSeek just open boxed themselves. They laid out their entire training pipeline. They detailed exactly how they go from the cold start phase to supervised fine-tuning, all the way to reinforcement learning using GRPO. But the most valuable part of this update isn't the success stories, it's the failures. Learning from failure, DeepSeek explicitly discussed techniques they tried that failed. They talked about trying Monte Carlo tree search, MCTS, and having it not work out the way they hoped. They discussed their attempts at process reward models, PRM, and the issues they faced there. Do you realize how rare this is? Companies like OpenAI or Google almost never publish their failed experiments. They want you to think everything they do is magic. DeepSeek is basically saying, hey, we tried this cool thing, it broke. Here is why. Now there's been a lot of buzz online about why they would do this. Why give away the secrets? Rumors suggest that this level of transparency is actually a flex. The speculation is that if they are willing to share exactly how R1 works, down to the failed experiments, they must already have something much, much better in the lab. Some reports claim that a V4 model is right around the corner. The thinking goes, this is old tech to us now, so you can have it. Whether that's true or not remains to be seen. But it has certainly everyone thinking that the next release is going to be massive. We need to circle back to Confucius for one final mind-bending concept. We talked about memory, but there is another mechanism in the Confucius SDK that points toward the future. The meta agent. This is where things get a little sci-fi. The problem with building AI agents right now is that it is very manual. A human developer sits there and tweaks the prompts. They say, okay, use this tool for searching. Use this tool for file editing. They run a test, it fails. They change the prompt. They try again. It is slow and efficient. Confucius introduces the idea of a meta agent that designs the agent. Instead of a human manually tuning the system, the meta agent uses LLM-driven optimization to propose configurations. It looks at the task, proposes a structure for the agent, runs tests, inspects the results, and then iterates on the design automatically. It's basically an AI that builds other AIs. It optimizes the toolset. It optimizes the prompt structure. It tunes the parameters. This allows the system to evolve faster than a human team could ever iterate. And the results speak for themselves. When they tested this, specifically on benchmarks like SWE Bench, which tests software engineering capabilities, the results were stark. They took a model, Falcon H1R-7B, and wrapped it in this advanced Confucius scaffold. Then they compared it to much larger models. The tiny Falcon model, when equipped with the Confucius scaffold, actually started outperforming models that were significantly bigger than it. The data showed that the scaffold, the memory, the tools, the meta-optimization, mattered more than the raw size of the brain inside the jar. They even tested tool sophistication. They found that simple agents just dump output and hope for the best. But when they added advanced tool handling and recovery logic, the ability for the agent to realize it failed and try a different way, the success rates skyrocketed. For example, on one test set using Claude 4.5 Sonic, a hypothetical high-end model used in the comparison context, adding better tool handling moved the success rate from around 44% to over 51%. That is a massive jump just from changing the system, not the model. Part 6, Conclusion, the new rules of the game. So, what does all of this tell us? It tells us that the era of lazy AI development is over. You can't just train a giant model, release it, and expect to win. System over size. As Confucius showed us, a smart system, scaffold, with a good memory, can make a small model perform like a genius. Efficiency is king. As Falcon H1 showed us, specialized architectures with massive context windows are going to challenge the massive, expensive models. Transparency weapons. As DeepSeek showed us, sharing your secrets, even your failures, is the ultimate power move, accelerating the entire open source community while leaving competitors guessing what you have next. We are moving into a phase where AI agents aren't just chatbots anymore. They are complex engineered systems with working memory, self-correcting mechanisms, and the ability to design themselves. And the craziest part? A lot of this tech is being open sourced right now. If you are a developer, now is the time to start looking at how these agents are built. not just which model they use. Check out the Confucius SDK. Read that 80-page DeepSeek paper. The tools are there. Thanks for listening to this deep dive. It's been a crazy week in AI, and I have a feeling next week is going to be even wilder.